what we're going to do in our penultimate topic for today is change that cornerstone of the games that we've looked at so far. The very, very first topic that we went through, that very, very first slide that I gave to you, it said static games of complete information. And again, when we looked at dynamic games, we looked at dynamic games of complete information. Now, we did change that, if you remember, ever so slightly, when we looked at the idea of the chain store paradox. We said, well, one way of resolving the chain store paradox was maybe to introduce a little bit of information asymmetry. But only introduced that to you as an aside. Now what we're going to do is look more explicitly at this topic of information asymmetry. When these games are played, when the players know different things, when there is not complete information. Now, information asymmetry is something that you've already covered in Teaching Block 1. When you looked at the market for lemons, when you looked at signaling, the Spence model. All these ideas around information asymmetry. And indeed, I'll talk towards the end of the lecture about signaling, not in terms of education and the Spence model, but in terms of firms and how they send signals to other firms. But again, we'll return to that a little bit later. So it's not something that you've not already been exposed to. But when we look at information asymmetry, things change. We want to look at equilibrium outcomes. That part doesn't change. And the way that we've identified equilibrium outcomes is that the players within the game will want to choose optimal responses. And we've used the Nash equilibrium, or refinements upon the Nash equilibrium concept, to identify our equilibrium outcomes. Well, when we start looking at games where there is information asymmetry, that is, the players know different things, then we've got to refine, we've got to change our equilibrium concept slightly. And we're not going to define or use the idea of a Nash equilibrium, and not explicitly a Nash equilibrium, but in these games where players know different things, where they don't know for sure what their other players do, they don't know for sure what their outcomes, their payoffs are going to be. They will have expectations of the outcomes of the game, and they will have beliefs. And as such then, our equilibrium concept won't be a Nash equilibrium, but rather it will be what's described as a Bayesian Nash equilibrium. Because these games where there is information asymmetry are known as Bayesian games. And in a Bayesian Nash equilibrium, players again will want to choose optimal responses, but this will take account of the players' beliefs, their expectations, what they think is going to happen. Because with information asymmetry, they cannot guarantee what's going to happen. So, in a nutshell, that's what we're going to do in here. We're going to be looking at games, both static games and dynamic games, where players know different things, where there are hidden moves. And not all players can observe these moves. And in these sorts of games, the outcomes that we'll identify are described as Bayesian Nash equilibrium. So, that's then an overview of what we're going to do for today's lecture. Now, to start off, to introduce you to the basic principles, the basic ideas, I'll make it nice and easy, and we'll start off with a static game. Remember, static games are games where players move at the same time. So in this static game, it's a refinement upon a battle of the sexes, or a game where a man and a woman are choosing where they want to go for the evening. Now in this game, and we'll call it friends or enemies, a man and a woman are deciding where they want to go for their New Year's Eve entertainment. And they have one of two choices. They can either go to a very lively party, or they could go to a much quieter venue, go to a hotel for the evening. So those are the two possible venues that our players, the man and the woman, can choose to go to. But the woman absolutely doesn't want to go to the same place as the man. She absolutely wants to avoid it. However, the man would rather go to the same venue as the woman. But the crucial aspect of this game is that the man has a strong preference for venue. Whichever venue he prefers, and this will be determined by his character, whichever venue he prefers that more than going with the woman. Whereas for the woman, what matters more for her is that she avoids the man. But just remember this part in the game as well. The man has a strong preference for venue, whatever that preference might be. So, that's our basic setup. Where's the information asymmetry? Well, the information asymmetry lies in the fact that the woman does not know what the man's character is like. Because the man could be one of two modes. He could either be a party lover, where absolutely he wants to go to the party. That's the most important consideration for him. So he could be a certain type, a party lover. Alternatively, he might be a non-party lover. But all he wants to do is spend a quiet evening in the hotel. So the man can be one of these two types. A party lover or not a party lover. And this, though, is the source of the information asymmetry. The man knows perfectly what his character is like. He knows whether he prefers to go to the party or the hotel. But the woman doesn't. That's the information asymmetry. And it's that that drives the entire game. So, let's start off with, let's represent a simple perfect matrix if the man was a party lover. So, we've got our two players, we've got the woman, and we've got the man. We've got the two venues that they can choose over, the party or the hotel, and for the man, party or the hotel. And these numbers merely rank the outcomes in terms of their preferences. So, for example, let's take the man. Now, we said the man here is the column player. Remember, his figures, his payoffs are these second figures here. The 3 and the 2, and the 0 and the 1. Now, we said he had a strong preference for venue. And by strong preference, I'll actually be even more explicit. By a strong preference, I mean he has a dominant strategy. Doesn't matter what the woman does, he will always want to go. In this scenario, if he's a party lover, he would always prefer to go to the party. So there you go. This is the man going to the party. So where does he get his highest payoff? Well, there you go. It's these ones here, the 3 and the 2, when he chooses to go to the party. Now, we said he would rather go with the woman than without the woman. So when he goes to the party with the woman, he gets his payoff of 3. When he goes to the party without the woman, he gets his payoff of 2. But these are the highest two payoffs. If you compare these to when he goes to the hotel, 0 and 1. These at 0 and 1. 0 is less than 3. 1 is less than 2. So that's why he has his dominant strategy. That strong preference for going to the hotel. So, just so why we've got the 0 and the 1 there, well, we said the man would rather go with the woman than without the woman. So if they both go to the hotel, he gets a payoff of 1. If he goes to the hotel or she goes to the party, he gets a payoff of 0. So that's just the preferences for the man. The important thing is that as a party lover, he has a dominant strategy to go to the party. Now, if we look at the woman, it's not as crucial what these preferences are. But I did say that the woman wants to attend a different venue than the man. Now, in the very way that I've set these numbers up, you can also see that she would rather go to the party. She would rather go to the party than the hotel. But the most important consideration is that she doesn't attend the same venue as the man. But for the way I've set this game up, the preferences for the woman don't really matter. The crucial one is that, remember, is that dominant strategy for the man. If he's a party lover, he always prefers to go to the party. That's where he has his highest payoffs. So, that's what the matrix would be. if the man was a party lover. Now, both the man and the woman know what this matrix is. They know the preferences, and they know what the outcomes are. However, the problem is, the woman doesn't know whether the man has these preferences, or whether the man has these preferences. This would be the matrix if the man was not a party lover. If he would rather go to the hotel. And if he'd rather go to the hotel, that means there's a dominant strategy of attending the hotel. So if you looked at these payoffs, if you look for the woman, they are all exactly the same. We've got the same 2, 3, 4 and 0. So if I flick back to the previous one, you can see they're exactly the same. So the preferences for the woman do not change. Nothing changes for her. Where there's a difference is the payoff for the man. These 3, 2, 1s and 0s. Under this scenario, where the man is not a party lover, it means he has a dominant strategy to go to the hotel. So his highest payoff is when he goes to the hotel with the woman. That's where he gets his payoff of 3. His next highest payoff is where he goes to the hotel on his own. And then he gets his lowest payoff when he goes to the party on his own, and the next lowest payoff when he goes to the party with the woman. So that's the only change with this matrix, as it affects the man. Now, the information is interesting. Which one of these two matrices is the relevant one? Is the man a party lover, or is the man not a party lover? That's the source of it. The woman doesn't know which game is being played. So, what do? How do we find the outcome of this game? Do we look at one and find the Nash equilibrium, and then find the other one? So, well, that's the other Nash equilibrium. And maybe the outcome of this game would be one or the other. Obviously, it's not going to be that easy. We need to do something different. We need to go through and formally identify that Bayesian Nash equilibrium. So whilst the woman doesn't know the type of the man, and by extension, she doesn't know which of these two matrices is the relevant one, she does know 2 very important pieces of information. The first is that the man will be a party lover with a certain probability. That there's a chance that he'll be a party lover, there's a chance he'll be a non-party lover. But that probability that the man will be a party lover, we'll describe that as probability P, whatever P might be. There's a certain probability that that will be his type of a party lover. So that's the first piece of information that the woman knows. She knows that probability that the man is going to be a party lover. We'll define that as P. We also know, as we've said, and this is what makes the game that I've set up relatively straightforward, she also knows exactly what the man will do, contingent upon his type. Because if the man is a party lover, what will he always do? Please, someone tell me. He will, exactly. If she knows his type is a party lover, that man will always attend the party. We said there was a strong preference for venue. If he's a party lover, there's a dominant strategy to attend the party. So he will always do that. If he isn't a party lover, if the woman knows his type as a non-party lover, she knows that he will always choose the hotel. So those are the 2 bits of information that we do know, or that the woman does know. The man will be a party lover with a probability P, and she also knows, contingent upon his type, exactly what he will choose to do. So those are the 2 bits of information that we have. So, how do we bring this all together then to define our Bayesian Nash equilibrium? And just initially, to give you a definition of what a Bayesian Nash equilibrium is. This will be when all players are choosing an optimal response to the equilibrium strategies of all other players. Pretty much sounds like a Nash equilibrium so far. And then this part on the end, whatever the player's type. So that's what we need to set up. That would be a Bayesian Nash equilibrium. We identify these optimal strategies, but these optimal strategies are contingent upon the player's type. So the player's type in this case are the man being a party lover or not a party lover. So that's how we would formulate the full Bayesian Nash equilibrium. It's as simple as that. Now, the techniques, the mechanics of it aren't too different from what you've seen before. It's just the way that we set it up and the way we describe it at the end need to take account of that last part there, the player's type also. So let's think about these then. What we want to do is get the equilibrium strategies, both the man and the woman. Identify their optimal responses. Now, if you think about it, for the man, this is really, really straightforward. The way that I formulated this game, the way that it's set up, is if the man is a party lover, he will always choose to go to the party. That will be his optimal strategy. If the man is not a party lover, he will always choose to go to the hotel. That is his optimal strategy. So, for the man, it's really, really straightforward. There's no contention, no ambiguity. For the woman, though, it isn't so straightforward. Because why? Because of this information asymmetry. She doesn't know whether the man is a party lover or not. So her optimal strategies will be contingent upon what the man's true character type is. So that will be based upon her expectations, what she thinks the man is going to be. And that's what we need to identify. But if you think about it, there's a word that I've dropped in there as well. The equilibrium strategy for the woman should be optimal given her expectations. Now, where did we use that term before? We've dropped in that idea, expectations, when we looked at mixed strategies. When you couldn't know for sure what your fellow player was doing. Well, in this sense, this Bayesian, the way that we're setting up this game here, is very, very similar. The woman doesn't know what the man will be doing because she doesn't know his character type. But she will have an expectation of what he will do. And that expectation is driven by that crucial probability of P, the chance that the man will be a party lover. So, just to formally put this out there, we said the case of the man was straightforward. So if he chooses, if he is a party lover, he will always choose to go to the party. If he is not a party lover, he will always choose to go to the hotel. That's what we said previously. Let's just formalise it. I'll copy that down. But the case of the woman is the more involved with that. And this depends on her expectations. So, how do we calculate this? Well, firstly, what we need to do is calculate her beliefs, what she thinks the outcomes are going to be, but consistent with both the actions of the man, that if he's a party lover, he'll go to the party. If he's not a party lover, he'll go to the hotel. Not only consistent with that though, but also consistent with that probability P. The likelihood that the man actually will be a party lover. So we need to set her beliefs up that are all consistent with those facts. What the man will do, and also what she believes that crucial probability to be. So that's the first thing that we need to do. So, how have we said that? Well, we've said that the man will be a party lover with a probability P. And if he's a party lover, he'll always choose to go to the party. So that's the first thing we can say about the woman's beliefs. That with a probability P, She knows that the man will choose to go to the party. Those fit together. And we also know then, with a probability of 1 minus p, the man will choose to go to the hotel, because it's a probability of 1 minus p that the man will be a non-party lover. And if he's a non-party lover, he goes to the hotel. So those 2 points there are consistent with a woman's beliefs. That's exactly what she expects to happen. The man will go to the party with a probability p, and he will go to the hotel with a probability of 1 minus p. So that's then the first point. That is just formalising her beliefs, given the way that we've set this up. Given these beliefs, though, given what the woman thinks is going to happen, now we need to identify, propose various strategies of what the woman will want to do. Whether she herself will go to the party, or whether she herself will go to the hotel. Now, this part draws together same sort of principles as we saw when we looked at mixed strategy Nash equilibrium. And it all boils around to the woman doesn't know for sure what the man is going to do. And by extension, she does not know for sure what her payoffs are going to be. All she can deal in is expected payoffs. So that's what we need to find. The woman can go to the hotel and get a certain payoff. She could go to the party and get a certain payoff, a certain expected payoff. So what we need, though, are the expected payoffs of going to either venue. And in the most general sense, what will the woman want to do? She will want to attend that venue that gives her the highest expected payoff. If there's a greater expected payoff of going to the hotel, that's what she'll do. If there's a greater expected payoff of going to the party, that is what she'll do. She'll go to the party. But when these expected payoffs are equal, she's indifferent over which venue she will attend. So, that's what we need to do then. Identify, in the most general terms, the strategy with the highest expected payoff. Now, we've introduced this idea of P. That was the probability that the woman expected the man to go to the party. That was the probability that she expects him to be a party lover. Well, there will exist a certain value of P in the way that we're going to work this through, such that if P is greater than a crucial value we'll define as P star, that will then be that the expected payoff of going to the hotel is greater than the expected payoff of going to the party. And if that's the case, what would the woman want to do? Well, if the expected value of going to the hotel is greater, she will want to choose to go to the hotel. So that means the woman will choose to go to the hotel if the value of P is greater than that crucial value that we've defined as P star. Just simple as that. And what we're going to be working through is to find that crucial value of P star. So that's the first thing we can say. The expected payoff of going to the hotel is greater than the expected payoff of going to the party. That is, if P is greater than that crucial value P star, the woman will always choose to go to the hotel. And the reverse of that should be fairly obvious, that if the crucial value of P is greater than the actual value of P, so that observed probability is less than that crucial probability, it will mean that the expected payoff of going to the party is greater. If that's the case, the woman will always choose to go to the party. So you can see this. What does it involve? It involves finding that crucial value of P star. Now, once we've done this, we've then got that case in the middle. What happens if it's greater than P star, less than P star? But if P is exactly equal to that crucial probability, as I said, what does the woman want to do? She doesn't mind. The expected payoff to go into either venue is exactly the same. And that's what we need to find. That value there where it's indifferent. By extension, higher or lower, then it drives exactly what it's going to do, what the woman will choose to do. So that was our second point then. We now need to propose a strategy that's consistent with her beliefs. And that strategy will be dependent upon that crucial value of P star. If the value of P is greater than P star, she will choose to go to the hotel. If it was less than P star, she will always choose. Sorry, if it's greater than P star, hold on, let me check. Yeah. If it's right first time, if it's greater than P star, she will always choose to go to the hotel. If it's less than P star, she will always choose to go to the party. So, how do we find that then? Well, when we looked at mixed strategies, it was fairly straightforward. Well, this isn't too dissimilar. You just need to be careful where you get these numbers from. For the moment, I'll tell you what the expected value of going to the hotel and parties. The expected value of going to the hotel is 3p plus 0 times 1 minus p. Right, where does that, and that simplifies to 3p. Where does that come from? Okay. What I should have done at the beginning, by the way, have you all copied that table down in front of you? Maybe very quickly, there's a handout there for a little bit later as well. So there you go. So just to remind you, now remember this is what we're looking for. The expected payoff of going to the hotel is 3p. So where does this come from? Well, remember, this was the matrix if the man was the party lover. That, on the right, is the matrix, the payoffs, if the man is not the party lover. Remember, if the man is the party lover, here's the dominant strategy of going to the party. If the man is not the party lover, here's a dominant strategy of going to the hotel. So those were the two different games, or two potential games that we set up. But we said that the man will be a party lover with a probability of P. Therefore, this game is played with a probability of P. And then, by extension, this game is played the rest of the time. This is when the man is not a party lover, and that happens with a probability of 1 minus P. So, what were we looking at? We were looking at the expected payoff for the woman if she goes to the hotel. So, this is the woman. If she goes to the hotel. If she goes to the hotel there, or she goes to the hotel there. Well, she'll get a certain payoff if the man is a party lover. She would get a certain payoff if the man is not a party lover. So if the woman goes to the hotel and the man is a party lover, what do we know he will also do? If the man is a party lover, the man will always go to the party. So, in this one, that's what the man will do. He will choose this column here. And so if the woman goes to the hotel, whilst the man goes to the party, which he will always do if he's a party lover, the man will get a payoff of 3. And so there you go. That's where we got that value of 3 from. Now, why did we multiply it by that probability P? Well, she will get a payoff of 3 with a probability of P. That's the probability that the man will be a party lover. And they will be playing this game on the left. So that's where we get that 3p part. That's the first contingent payoff in our expected payoff of going to the hotel. So that's where the 3p comes from. But what about the next part, that 0 times 1 minus p? Well, what happens if the man wasn't a party lover, but instead we're playing this game here? And we will be playing this game when he's not a party lover, but with a probability of 1 minus p. So, the woman, if she chooses to go to the hotel, if the man is not a party lover, what will he always choose to do? Go to the hotel. So the woman is going to get a payoff of 0. So if the woman goes to the hotel, knowing if the man is a party a non-party lover, he will also choose to go to the hotel. She's going to get a payoff of 0. So there you go. That's where our 0 comes from. And how often will she get that payoff of 0? She'll get that payoff with a probability of 1 minus p. So that is where the expected payoff comes from either of these two matrices. Now, when we did mixed strategies, remember we put the p's and the 1 minus p, or the q and the 1 minus q on one single matrix. When we look at these Bayesian games, where the ambiguity arises is not what the payoffs are going to be, but it's which of these matrices we're playing. So there you go. That's the expected payoff for the woman of going to the hotel, which we simplified to 3p. So that was that part there. And in exactly the same way, we could calculate the expected payoff of going to the party for the woman as 2p plus 4 times 1 minus p. Which again, if you simplified it, comes to 4 minus 2p. I'll quickly go back to this one just to show you. So if the woman goes to the party and the man is a party lover, gets a payoff of, the woman gets a payoff of 2. If she goes to the party and the man is not a party lover, she gets a payoff of 4. So it's the 4 and the 2, weighted by 1 minus p and p. So 4 and the 2, weighted by 1 minus p and p. So again, that is where that comes from. So now we know, for the woman, her expected payoffs. We've gone to the hotel, it's 3p. Gone to the party, it's 4 minus 2. So what did we want to do? We then wanted to find that crucial value of p star. So what did we say we do? Well, we equate these two. So if you equate 3p and 4 minus 2p, that was the expected payoff of going to the hotel. That's the expected payoff of going to the party. Solve that. That gives us our crucial probability of p. And it tells us that when the man goes to the hotel, when the man is a party lover with a probability exactly equal to 0.8, the woman is indifferent. She doesn't mind what venue she attends, because both will give exactly the same expected payoff. But the way that we set this up, we said that when p was greater than that crucial value, so when p is greater than 0.8, the woman will choose to go to the hotel. If you think about it intuitively, what are we saying here? As p increases in value, that means it's more and more likely that the man will be a party animal, a party lover. He wants to go to the party. So as that probability increases, what does the woman want to do? Well, she doesn't want to go to the party because she knows the man is more likely to be there. So as p increases, she's more likely to choose to go to the hotel. That venue where the man isn't going to be. And for the woman, that was the important consideration. She doesn't want to go to the same place as the man. And then, the converse of that is when p was less than 0.8, the woman will choose to go to the party, because going to the party gives a higher expected payoff. And that, then, are the optimal strategies for the woman, contingent upon her beliefs, that are consistent with her beliefs. That probability p and her knowledge of what the man will do, dependent upon his type of character. And so, that is fundamentally what we need. Now, the final part, then, just that part for fullness, is if p exactly equals to 0.8, what will the woman want to do? Doesn't really matter. She goes to the party, she goes to the hotel. Both give exactly the same expected payoff. So, at that crucial probability, the woman is indifferent over what she wants to do. So now what we've done is we've worked through this and we've been through the mechanics of it. Now, what we want to do is formally put it all together and just present the Bayesian Nash equilibrium. Written out, it would be like this. Now what we said is this will depend, we need to find the optimal strategies for the man and the woman, but given their beliefs and given their character types. Now, for the man, there are no beliefs here. For the man, he knows, he's got full information. He knows exactly what the payouts are. There is no information asymmetry for him. So his optimal strategies are what we need to find. And we said, well, when the man is a party lover, he will always choose to go to the party. When the man is not a party lover, he will always choose to go to the hotel. However, for the woman, her optimal strategies are contingent upon her beliefs. And her beliefs depend on that crucial probability of 0.8. And so when P was greater than 0.8, she would always choose to go to the hotel. When P is less than 0.8, she will always choose to go to the party. And then when P was exactly equal to 0.8, she would randomise her behaviour, because both would give exactly the same expected pairs. Now, all that slide is doing is formalising all that I've worked through up until then. But that's the working out, but this here is the full and formal Bayesian Nash equilibrium. And it's as simple as that. That is what we do in a static game. Relatively straightforward? Yep. Not pushing the boundaries too far. Okay. Now what we're going to do is look what happens in a dynamic game. Well, dynamic games are where players take it in turns to move. And the dynamic game we're going to consider is that game of market entry that we've seen numerous times before, where we have an incumbent firm, an incumbent monopolist, and a potential entrant. That potential entrant who's thinking about entering up into the market and entering and setting up, I should say, in competition with the incumbent monopolist. So, this is a sort of game that we've seen before. The payoffs reflect that. The only slight difference, and again, maybe this will make it a little bit easier for you, what I've assumed is that there are potential profits in this industry of 10. And so, if the entrant, the potential entrant, enters the market and the monopolist acquiesces, they will split this potential profit equally. They'll both get 5. However, if the entrant stayed out, the monopolist would gain that full profit of 10. But as we know, in these games of market entries, what is the worst possible scenario? The worst possible scenario is that the entrant enters, the monopolist responds by fighting market entry, and in which case the profits of both firms are reduced all the way down. They get profits of -1. So that's our game of market entry. Now, if I had to throw that at you, what would be the subgame perfect Nash equilibrium of that game? Yeah, it's going to be. Yep. I mean, if you wanted to, you could work through it formally. Hopefully, you should know by now. This game of market entry that we've seen before, the only logical outcome when this game is played just the once, the subgame perfect Nash equilibrium is that the entrant enters the market and the monopolist responds by acquiescing. So in that case, the subgame perfect Nash equilibrium would be enter, acquiesce. So they both get a payoff of 5. Now, if you want to do, you could formally identify that by the process of backwards induction. But you all know what that outcome is. So that's the game of market entry that we've seen before. Now we're going to change it ever so slightly. Because now we're going to say that there's an opportunity for the monopolist, the incumbent firm within the market, to invest in sunk costs. And it will do this to deter market entry. So, for example, it could invest in excess capacity. It could invest in a heavy brand loyalty and advertising scheme that builds loyalty of customers to it. But this does, though, impose a sunk cost. Once this is spent, it doesn't matter whether market entry occurs or not. That expense has already been incurred. That expense has already been incurred. The monopolist cannot get this back. So there's a possibility, if the monopolist wants to deter market entry, it can invest in sunk costs by, as I said, excess capacity, building up brand loyalty through a heavy advertising scheme, whatever. So that's the possibility. Now, if the monopolist does do this, it imposes a cost, regardless of whether market entry occurs or not, and this imposes a cost of 2. And that is flat whatever the scenario is. And the monopolist can never, ever get this back. So that's the idea of a sunk cost. So take that, and we'll just take that back to our game. What does it now mean? Well, the point of investing in a sunk cost is it can deter market entry. Why does it do that? Because it makes it easier to fight market entry if it does occur. If you've invested in excess capacity, or you've invested heavy advertising scheme that allows you to build up brand loyalty, well, as soon as a rival enters the market, you can then exploit your excess capacity, or you can exploit your brand loyalty, and you have an advantage over the incoming fee. So that means if market entry does occur, and these sunk costs have been imposed, the monopolist can make a net gain of 5. So rather than having profits of -1, it can add 5 to that. So it will then get its market share. So that's the effect of sunk cost. Automatically imposes a sunk cost of 2, regardless of whether market entry occurs. But if market entry does occur, and the monopolist chooses to fight, it can nevertheless make a net gain of 5, over and above its sunk cost. So that's the gain that we've done, and it changes it ever so slightly. So that is now the gain with these sunk costs. So if the entrant chooses to stay out, the payoffs previously were 0 and 10. Well, now, if sunk costs have been incurred, the payoffs are 0 and 8. So the 10 previously minus the 2 sunk costs. If the entrant chooses to enter and the monopolist acquiesces, rather than the payoffs being 5 to each, the entrant still gets a payoff of 5, but the monopolist now gets a payoff of 5 minus the 2 sunk costs. So it now only gets a payoff of 3. And then lastly, if the entrant enters and the monopolist chooses to fight, the payoff to the entrant is still -1. It gets the most detrimental outcome, but we said there's then a net gain of 5. So 5 minus the 1, so the payoff would then be 4. So that is what happens, that is what the gain would be if the sunk costs were incurred. So that is one gain, but we've also seen another gain, where sunk costs haven't been incurred. That standard gain of market entry. Yes, this is the important part. I know some of you have copied this down, but the handout, these two diagrams are on either side. But what can we say about this gain here? We said in the initial game, where sunk costs weren't incurred, the sub-game perfect Nash equilibrium was for the monopolist to acquiesce, always allow market entry. Here though, where sunk costs have been incurred, it's slightly different. The monopolist will now always choose to fight, because if market entry occurs, if the monopolist acquiesces, it gets a payoff of 3. If it chooses to fight, given that it's invested in these sunk costs, it can now get a payoff of 4. So, the monopolist, if it's incurred sunk costs, will always choose to fight market entry. By extension then, if the monopolist will always choose to fight market entry, what will the entrant choose to do? It enters, it will get a payoff of -1. It stays out, it's going to get a payoff of 0. So again, we can see how the sub-game perfect Nash equilibrium of that game changes, all down to these sunk costs. But now, though, I want to bring it back around to this idea of information asymmetry. So, if we say that the monopolist, so if we allow the monopolist to have invested in sunk costs, if we allow the monopolist to have invested in sunk costs, we will describe the monopolist as being strong. That's our descriptor. The monopolist will be strong. If, though, the monopolist has not invested in sunk costs, we will describe the monopolist as being weak. Where is the information asymmetry? The information asymmetry is that the information asymmetry is that the entrant does not know whether the monopolist has invested in these sunk costs. It does not know whether it's invested, for example, in excess capacity, or it's built up this brand loyalty. The monopolist itself obviously does know. It knows whether it's strong or weak. Information asymmetry is that the potential entrant doesn't. All it can do is have an expectation, a belief that the monopolist is either strong or weak. It's invested in sunk costs or it hasn't. And so we'll say that it believes that the monopolist is strong with a probability of P. And similar to what we've done before, it's this crucial probability of P that will drive all of our expected outcomes. So, that's what we've said. That's what we've set up. We've got two games. We've got that standard game of market entry that we saw first of all, and then we've got that game of market entry with sunk costs. Which of these two games are we going to be playing? That's something we don't know. But what we do know, though, is that the monopolist will be strong with a probability of P. So if the monopolist is strong, what did we say would happen? If the monopolist is strong, it will always choose to fight market entry. So if market entry does occur, we know with a probability P that the firm, the monopolist, will choose to fight. With sunk costs, that was the optimal strategy. The flip side is, though, that the monopolist will be strong, the monopolist will be weak with a probability of 1 minus P. And if the monopolist is weak, how would it respond to market entry? By acquiescing. So again, we can say that monopolist will choose to acquiesce if market entry occurs with a probability of 1 minus P, because that's what it will always do if it is weak. So, this then comes to the handout. That's essentially on the left and on the right. The labels ever so slightly different, but those are the two games that we've seen. This, on the left, is the game that occurs if the monopolist is weak. So in terms of the descriptor, for MW, if the monopolist is weak. And if the monopolist is weak, it hasn't invested in sunk costs. And so we then get our initial payoffs, where they both split that profit of 5. On the right-hand side, this is the game where the monopolist is strong. So MS denotes that the monopolist is strong. This is where sunk costs have been incurred. So we can see here the payoffs are slightly different, where that sunk cost of 2 has been incurred. So those are the two games. But the part about information asymmetry is that there is this unobserved action at the top. Has the monopolist invested in sunk costs? Entrant doesn't know. So which of these two games? Is it the left or is it the right that's being played? That's the source of the information asymmetry. So, what can we say about this game then? Well, let's think about the expectations of the firm. Well, it knows for sure, absolutely, if this monopolist was weak, it would choose to enter. Because it's weak, the monopolist will concede to market entry. The problem is, does it enter or does it stay out? That's what the entrant needs to choose. If it enters and the monopolist is weak, market entry will be conceded. If it enters and the monopolist is strong, it will fight. So we'd only want to enter if it's not going to be met by an aggressive response. That's the crucial decision that this potential entrant needs to take. Does it enter or does it stay out? And what factors does it use to make that decision? It looks at expected payoffs. If I enter the market, what's my payoff likely to be? If I stay out, what is my payoff likely to be? And it looks at the relative magnitudes of these. Naturally, if the expected payoff of entering the market is greater than the expected payoff of staying out, the entrant will choose to enter. Remember we said expected payoffs? And why have we got expected payoffs? Because the entrant doesn't know how its entry is going to be met, whether it will be fought or acquiesced. Because there's ambiguity over a weak or strong monopolist. So again, just formalising it, just setting it up in the way that we did previously, we will say that there will exist a crucial probability of P star, such that if P is greater than P star, the expected payoff of staying out is going to be greater than the expected payoff of entry. And if the expected payoff of staying out is greater, that's exactly what the entrant will do. It will choose to stay, and vice versa. Now, the way that we would formulate these is in exactly the same way as we saw with our Bayesian Nash equilibrium previously. The only difference is, remember, this is not a static game, but rather a dynamic game. And in dynamic games, we don't use the concept of a Nash equilibrium, but rather a subgame perfect Nash equilibrium. So that then is the only subtle difference. And the idea, when we look at subgame perfect outcomes, they need to be optimal strategies, not just within the game in its entirety, but in all subgames also. So again, that's the only subtle difference. And that's just a semantic thing as we describe the equilibrium that we get here. So it's not necessarily a Bayesian Nash equilibrium, but rather it's a perfect Bayesian Nash equilibrium. But apart from that, the logic that lies behind this is still exactly the same. We want to find expected payoffs. By extension, we want to find that crucial probability of P star. So, that's what we're going to do. All relatively straightforward. So, how do we find this then? How do we formulate that Bayesian Nash equilibrium? Well, for the monopolist, what it will choose to do, and remember, go back to that definition that I gave you previously, that these optimal strategies depend not only upon your beliefs or expectations, but also upon the player's type. And for the monopolist, it can be strong or weak. So what are its optimal strategies? Well, if the monopolist is strong, we said that it will always choose to fight market entry. We said if the monopolist was weak, it will always choose to acquiesce to market entry. So remember, if market entry doesn't occur, there's no choice for the monopolist to make. It's only after market entry has occurred. And given its type, strong monopolist, one who has invested in sunk costs, will always choose to fight. A weak monopolist, a monopolist who has not invested in sunk costs, will always choose to acquiesce. And the remainder of identifying this subgame perfect, or this perfect Bayesian Nash equilibrium, is just finding that crucial probability of P star, such that the expected payoffs of staying out of the market for the entrant is exactly equal to the expected payoff of entry, the market for the potential entry. And that's all we need to do for this final part. Identify that crucial probability. So, how do we find those expected payoffs? Well, if you look at the diagram, I won't put it up on the board because it should be fairly obvious for you. For the potential entrant, it does not matter whether the monopolist is weak or strong. If it stays out, it always gets a payoff of 0. So the expected payoff is 0. The expected payoff to staying out is always 0. The expected payoff of entering, and again, I'll tell you what it is, and then we'll relate it back to the diagram. The expected payoff of entering is 5 times 1 minus p plus minus 1 times p. Why is that the expected payoff of entering the market? Well, if the monopolist enters the market, we've got two games here. We've got this game here, where the monopolist is weak. We've got this game here, where the monopolist is strong. Now, if the entrant enters the market and the monopolist is weak, what did we say the monopolist would do? Would always acquiesce. Hence, this is our sub-game perfect outcome there. So, if the monopolist is weak, market entry will be met by acquiescing, and the entrant will get a payoff of 5. That's our 5 there. And where do we get the... Whoops. And then the 1 minus p, that was the probability that the monopolist is weak. That is the probability that we're playing this game on the left-hand side. Where do we get the minus 1 from? Well, if the entrant enters the market and the monopolist is strong, its entry will be met by an aggressive stance, by fighting. In which case, the entrant gets a payoff of minus 1. And it will get a payoff of minus 1 whenever the monopolist is strong. And it's strong with a probability of p. So hence, that is our expected payoff, which we can simplify to 5 minus 6p. So now we know for the entrant what the expected payoff is for staying out, 0. We know what the expected payoff is for entry. It's 5 minus 6p. And so, what did we say we do? We said that we want to find that crucial probability. What happens if one is greater than the other? If it's greater than that crucial probability? Well, work through the algebra for yourself. 0 and 5 minus 6p. And that will say that the expected payoffs are the same when p, that crucial probability, equals 0. Equals 5, 6, I should say. And so, if p is greater than that, we have that the expected payoff of going to the expected payoff of entering is greater than the expected payoff of staying out. When that inequality is reversed, we just get the reverse situation. When p is less than 5 over 6, the expected payoff of entering the market is greater than the expected payoff of staying out. And so, the entrant would choose to enter. All boils down to identifying that crucial probability. And the way we do that is by equating the expected payoffs. In this example here, it comes out just to be 5 over 6. And so, either side of that, then we know exactly what entrant will choose to do. And that then specifies for us the full, everyone finished that? That then specifies the full Bayesian Nash equilibrium. Which then is, we want to do it for both the monopolist and the entrant, contingent upon the type. So find the optimal strategies contingent upon the type. And so the type, remember, is the monopolist being weak or strong. And so, formally, we'd say that when the monopolist is strong, it will always choose to fight market entry. When the monopolist is weak, it will always choose to acquiesce, to accede to market entry. And then, for the entrant, this is that last part that we found, we said when P, when the perceived probability that monopolist is strong was greater than 5/6, the entrant would choose to stay out because the expected payoff was greater. And in the same way, whenever P was less than 5/6, so the monopolist is believed to have not invested in sunk costs, with that probability less than 5/6, the entrant will choose to enter. And then, when that perceived probability was exactly equal to 5/6, the entrant would randomise between what it does between staying out and entering, because the expected payoffs are the same. And so that there is the full Bayesian Nash equilibrium. And note, though, that it doesn't only depend upon a certain probability. When we looked at games of complete information, and we looked at mixed strategies, we said that the mixed strategy just involved a certain set of probabilities. For the full Bayesian Nash equilibrium, it's not just these probabilities that are important, but it's also that you need to set out the actions given the players' types. So, that is by way of introduction to this idea of dynamic games. Now, what I want to do is reintroduce that idea, as I alluded to at the beginning of the lecture, about signalling. And signalling is something that you've already seen in your micro lectures and teaching block 1. And in particular, when you looked at the Spence model and education. And what does education do? Why do certain groups of workers invest in education? Because it sends a signal. And if you cast your mind back there, again, a crucial part of that, we have high productivity and low productivity workers, is that education is cheaper to acquire the high productivity workers. There's a different cost. But it's all driven by this idea of information asymmetry, because employers do not know whether workers are high productivity or low productivity. What wage do they pay them? That's why workers invest in education, to send that signal. Well, it's exactly the same principle that we're going to now just extend this dynamic game. Because we've said, when we found this crucial Bayesian Nash equilibrium probability, that P, that determined whether the entrant stayed out of the market or not. Now, as that value of P increases, as it's more and more likely that the monopolist is strong, that's P increases, it's more likely that the entrant will stay out of the market. Yeah? So you can see, by extension, what does this mean? Well, it would mean that the monopolist would want that value of P to be as high as possible. It would want to influence that value of P, because the greater it is, the less likely is the entrant going to be to enter the market. So, how does it do that? How can it influence that value of P? Well, it can do it by sending a signal. And a strong monopolist would want to do exactly that. The strong monopolist knows that it's invested in sunk costs. And it would want to signal this to potential entrants. Look, it's pointless you enter in the market. I've invested in sunk costs. If you do enter, absolutely, I'm going to fight you. It would want to convey that message. It would want to convey that message by sending some sort of signal. But in the same way, the weak monopolist would also want to send a signal. It knows that it hasn't invested in sunk costs, but it would want to pretend that it had. It would want to send a signal, oh, actually, must misinterpret this, I have invested in sunk costs. And if it did that, again, it would influence that value of P. If the entrant receives that signal, it thinks there's the higher probability that monopolist is strong, it's less likely to enter. And that is what the monopolist wants. It wants to keep the entrant out of the market. So, that's where signalling comes in. And by sending a signal, it can influence this value of P. It can make this value of P increase, and hence deter market entry, make market entry less likely. So, that's the idea then. Can, and in particular this relates to the strong monopolist, can the strong monopolist send that signal? Send the signal that it's invested in sunk costs. But the whole point about this, in the same way as you would have seen signalling in the spends education model, that it needs to be more expensive for the weak monopolist. It must be cheaper for the strong monopolist to send this signal. It only logically makes sense if that's the case. If it costs the same for both of them, they'll both send it. So it needs to be cheaper for the strong monopolist. Now, the way that we've set this up, does that make sense? Well, of course it does. We've said, what's the idea about sunk costs? That the firm, for example, the monopolist, has invested in excess capacity, or it's built up some sort of brand loyalty. Well, what could it do? Well, what it could do to send that signal, it could have a targeted publicity campaign, targeted at its own existing customers. And that sends a very, very clear signal to the market. And the reason I can do that is because I've built up this base of customers. And so for the monopolist, who's strong, who has invested in brand loyalty, who's invested in sunk costs, that is then cheaper to do. So a targeted campaign that sends a signal is more expensive for the weak monopolist because they haven't built up the brand loyalty. So in that sense, the way that we've set this up makes perfect sense. That it's easier, it's cheaper for the strong monopolist to send the signal. So, that's what we know. We've got our setup. Monopolists could be strong or weak. But they both want to send this signal to infer, to give the impression that sunk costs have been invested in. And this signal, if it's sent, will be observed by the potential entrant. The crucial part here, it's cheaper for the strong monopolist to send the signal. It's cheaper to send it if you've already invested in these sunk costs. And that is going to be crucial to all of this. It's cheaper for the strong monopolist to send that signal. In the same way as you would have seen high productivity workers accumulating education in the Spence model. That's it. Cheaper for certain groups than others. Here, it's cheaper for the strong monopolist to send the signal. The signal that is invested in sunk costs. That it is indeed a strong monopolist. So, what does that mean then? Well, given what we've set this up, or the way that we've set this up, the important thing is if the entrant does observe the signal, it's more likely that the monopolist will be strong. And if the monopolist is more likely to be strong, it's less likely that the entrant will enter the market. And that is what this boils down to. Send that signal to increase that value of P. So what does this mean? Well, it means that when the entrant is thinking whether it enters the market or not, it needs to look, have I received this signal or not? Have I seen this signal? Because if it has, that information then needs to be incorporated into its decision-making process. Because if that signal is received, it means that the monopolist is more likely to be strong. And that, by extension, affects what the entrant will do. So it means if the signal is received, that value of P needs to be updated. And that's what this next part is going to be about. It's how is that value of P updated. So, what I'm going to show you, might have the notes in front of you. What I'm going to show now might look a little bit daunting, a little bit of a probability. I swear this is really, really straightforward. Okay? It isn't difficult. Okay? It might look daunting, but it isn't. I promise. Okay. We're going to update that value of P. Now, what is P? P is a probability. But what we're doing, we're saying, what's the value of P? Remember, what is P? P is the probability that the monopolist is strong. That is what the entrant is trying to identify. But we're now going to change that slightly. We're going to update that value of P. What is the probability that the monopolist is strong, given that I've received that signal? That's not an unconditional probability of what P is. That is a conditional probability. And in statistics, to identify a conditional probability, we can use very simply what's known as Bayes' theorem. So the updated value of P, remember P is the probability that monopolist is strong. That's what P was. But now we're looking at the updated value of P, which is a conditional probability. So it's the probability that the monopolist is strong, given that the signal has been received. So the probability the monopolist is strong and a signal has been received. So that's all we want to identify. We're not looking at P now, we're looking at this updated value of P. And that is what the entrant will use in its decision-making process. So that's the starting point. Monopolist is strong given that the signal is received. Well, according to Bayes' rule, if you want to identify a conditional probability, you don't need to worry where this comes from. This is just Bayes' rule. So, the probability that the monopolist is strong, given that the signal has been received, is equal to the probability that the signal has been received, given that the monopolist is strong, multiplied by the probability that the monopolist is strong, and all of that divided by the probability that the signal is received. So that's just Bayes' rule. You might have covered it in stats. Did you cover stats in your first year? No, but I'm not going to go through and do it. It makes no difference whatsoever. That is just what Bayes' rule is. If you want to work out what a conditional probability is, it would be equal to that. Because you can't work out that directly. You can't just take a number and drop it in. It's conditional upon this signal being received. So, any conditional probability here, that's what it's equal to. So, just take my word for it, and that's what we need to find. So, rather than one thing, we need three separate things. So, when we look at this, two of those are straightforward. The probability that the signal is received and the monopolist is strong. We'll come on to that idea. That's straightforward. That really is straightforward. The probability that monopolist is strong. Well, we already know that. That's P. Again, that's straightforward. What isn't as straightforward, necessarily, is that one there on the bottom. What is the probability that the signal is sent? Well, the probability that the signal is sent, again, is a contingent probability. Who would send the signal? Well, the weak monopolist would send the signal, or the strong monopolist would send the signal. So the probability that the signal is sent is the probability that the signal is sent, given that monopolist is strong, multiplied by the probability that the monopolist is strong. Then add to that the probability that the signal is sent, given that monopolist is weak, multiplied by the probability that monopolist is weak. I mean, in many ways, that's the same sort of idea when we looked at expected payoffs. There's a certain probability that the signal will be sent if the monopolist is strong. There's a certain probability that the signal will be sent if the monopolist is weak. Well, these contingent probabilities are then just weighted by the probability of the monopolist being weak or strong. So that is what the probability of the signal being received is. So that bit on the bottom, we can replace it with those four terms there. That multiplied by that, plus that multiplied by that. So that is what our updated probability is. Now, I said it looks daunting. It really, really isn't. Honestly, it isn't. So, what have we got here? So, remember, what we're looking at is how the entrant updates that value of P. So, what's the probability Not just the monopolist being strong, the monopolist being strong given that that signal has been sent. Well, that simple adaptation of Bayes' rule, it's equal to that term there. That is what the updated probability is. Yep. So, I said previously that what underlies this is that it should be easier for the strong monopolist to send that signal. And the way that I formulated this in terms of an advertising campaign, targeted at existing customers. Let's take this one step further. Let's say, just make it nice and simple, that the cost of sending this signal for the strong monopolist is 0. If it's invested in sunk costs, the cost of sending that signal is 0. Now there will be some positive cost for the weak monopolist, the monopolist who has not invested in sunk costs, but if those sunk costs have been incurred, it costs the monopolist 0 to send that signal. Yeah? So what does that mean? Well, if the cost is 0 to sending the signal, the natural extension to that argument is that the strong monopolist will always send the signal. So if you've invested in sunk costs, and it's costless to send that signal, you will send that signal. So the entrant will always know that you've invested in sunk costs, that you genuinely are a strong monopolist. And by extension, you will fight market entry. So, we'll do that, and then we'll go back to that updated probability. So, the cost of sending the signal for the strong monopolist is 0. And as such then, the strong monopolist will always send the signal. Or it sends it with a probability of 1. Yep, you always send it probability of 1. So, let's go back to that updated probability here. And let's start picking off some of these terms here. Well, we've said that the probability that the signal will be sent if the monopolist was strong was 1. The strong monopolist would always send the signal. So if you've got here, well, the signal, given that monopolist is strong, that term there is equal to 1. Signal that monopolist is strong, that term there is equal to 1. And we already know, so those terms are going to drop out, it's going to be equal to 1. Well, we also know, what is that term there? The probability that monopolist is strong. That was our value of P. Probability that monopolist is strong. That's our value of P. And also, what's the probability that the monopolist was weak? That was, it was equal to exactly 1 minus P. So we know what that term is, we know what that term is, and we know what that term is. Those are P, and that's, last one, is 1 minus P. So our updated probability, so the probability that monopolist is strong, given that the signal is received, then comes down to that expression there. And that is the updated value of P that the entrant would use. And from this, we can now see why it's important that this signal, the cost of this signal, is different between the weak and strong monopolists. This is what it all boils down to. So let's think, what would happen if the weak monopolist, let's take two extremes. What would happen if the weak monopolist, and I want you to think about this intuitively, not just by looking at the equation. What would happen if the weak monopolist never ever sent a signal? Intuitively, what would it mean? Would that value of P ever be updated? What will the strong monopolist always do? Send a signal. Now, if the weak monopolist never sends a signal, what does that mean to the entrant? If it receives a signal, the only person who could have sent that would be a strong monopolist. So the chances of the monopolist being strong is 1. It's guaranteed. So therefore, that signal doesn't help the weak monopolist in any case. It never ever sends it. It reveals itself that it hasn't invested in sunk costs. And given that the strong monopolist will always send a signal, it rules out that market entry will not occur. So, what has that got to do with that part there? Well, if the weak monopolist never sends the signal, look at this updated value of P. It's that one there. The probability that the signal is sent given that monopolist is weak. So the weak monopolist never sends a signal, that probability is 0. So that is P plus 0 times 1 minus P. So that is P over P. So our updated value of P then becomes 1. Given that signal is received, what's the probability of the monopolist being strong? It's 1. It's absolutely guaranteed. There's no chance, 0 chance, of the monopolist being weak. So there you go. That's why that term there is crucial. That if the weak monopolist never ever sends a signal, it rules out that the monopolist, if the monopolist never sends that signal, it rules out that the entrant will stay out of the market. It will always enter, because it will know that the monopolist is strong or weak. So, that's one case. What would happen though? Let's take the other extreme. Not that the weak monopolist would never send a signal, but what would happen if the weak monopolist was just as likely to send a signal? Would this impart any extra information? Again, would P be updated? Well, if the weak monopolist was just as likely to send a signal, i.e. it would always send a signal, go back to that part there. What's the probability that the signal will be sent given that monopolist is weak? Well, if it was costless for the weak monopolist as well, if it costs exactly the same for the weak as the strong monopolist, what would that probability there be? Well, that would also be 1. We've said that the strong monopolist will always send a signal. Well, if the weak monopolist is just as likely to send a signal, it means that value, that probability there, is 1. Now what happens when that probability is 1? You get P divided by, then P plus, that's 1 times 1 minus P. So that's P plus 1, that's P plus 1 minus P. So that then gives us P plus 1, that gives us 1 on the bottom. So that's P divided by 1. So our updated value of P doesn't change, it's still P. So it does not then confer any extra information. So what's the point of having the signal? And this is it. This is the point of all of this. It's only when the signal is more costly for the weak monopolist to send that it conveys any additional information. And whenever the probability that the signal will be sent by the monopolist, given that monopolist is weak, is any value between 0 and 1, it's then and only then is that value of P updated. And it's this updated value of P that then enters into the calculation for the entrant. It doesn't look at P, but rather it uses that updated value of P, which is contingent upon the signal being received. Hence, what would we say then? Formally then, the full Bayesian Nash equilibrium would be this. Firstly, the monopolist chooses its optimal strategies. We said that the strong monopolist will always choose to send a signal, and it will always fight market entry. So those are its actions, contingent upon its type. If it's strong, send the signal with a probability of 1. If market entry does occur, it will always choose to fight. However, the weak monopolist will send the signal with some probability. If initially P is less than 5 over 6, and if market entry does occur, it will always choose to acquiesce. Remember, we get that value of 5 over 6, that, remember, is what we showed previously. But it will only want to update that value of P, send the signal if that crucial value is less than 5 over 6. If P, the probability that the entrant thinks the monopolist is strong, is greater than 5 over 6, it doesn't need to send the signal, because it already believes that the monopolist is strong. It's only when it believes it's weak that there's any extra information, anything to be gained from sending that signal. And then, lastly, for the entrant, if it receives no signal, it will choose to enter. If, though, depending on that updated value of P, whether it's greater or less than 5 over 6. Remember, if it doesn't receive the signal, why does it enter? Will enter if there is no signal. Why does it do that? Why does it always do that? Given what I've said. Because what will the strong monopolist always do? Send a signal. Therefore, if you don't receive a signal, it means the monopolist can't be strong. If the monopolist isn't strong, you know it's going to acquiesce to market entry, that it's weak. Hence, you'll always choose to enter. However, this comes apart if a signal is received. Who does that come from? Does it come from a strong monopolist, or does it come from a weak monopolist? That's the nature of the information asymmetry. The entrant does not know. So, then we go through that updating procedure. And we get the updated probability, and is it greater or less than 5 over 6? If that updated value of P is greater than 5 over 6, again, this is our expected payoffs, the entrant will choose to stay out. If that updated value of P is less than 5 over 6, it will choose to enter, because it will believe that the monopolist is more likely to be a weak monopolist and will acquiesce to market entry. And then lastly, if the updated value of P exactly equals 5 over 6, it will randomise between, the entrant will randomise between staying out and entering the market.